Hi, good afternoon. Can you guys hear me? We'll just hold on for a couple of minutes. We'll start exactly at 3 or 2.
Hey Karthik, we can actually hear you.
Thanks. Just wait for a couple of minutes. We'll start sharply at 3, 2. Hi. Good afternoon. Let's get started. I welcome you all to our first webinar in AutoZar, hosted by Ansett. It's been a lovely day. Thank you so much for joining us. It's a pleasure hosting you all. We have around 200 plus registrations from 60 plus companies, and we hope to live to your expectations. We are also live on YouTube. So quick introduction about Ansett. Ansett is primarily a tooling and engineering service company for the automotive and the aerospace industry. We have been in the market for 15 plus years, 120 plus employees, and we work on various projects like product development. We build products for our customers, like say database editors. We build testing tools, etc. We also do customized tool development, like say building IDEs, building test automation processes for our clients. We also do consulting and training services. And a small bit introduction about me. I'm Dr. Karthik, 16 years of experience in research. I'm part of Ansett research team. All these years, I've been spending most of my time in researching areas like radio frequency electronics, automotive, and industrial IoT. That's a quick background about us and myself. Now let's just get into the webinar. So what is the motto of the webinar? We don't promise you at the end of the webinar, we will make you experts in AutoZar. None of us are. AutoZar is almost a 25,000 plus document. So none of us can become experts in AutoZar, at least until we spend a couple of years in the company. But what is the objective of the webinar is to Google enable you in AutoZar. So at the end of this webinar, if you are able to find some words related to AutoZar, or if you want to search for something in AutoZar, you will be able to pick up references and you will be able to visualize what we are discussing. All right, so that will be the whole objective of this webinar to start with. And the agenda, we'll cover 3 important topics. We'll start with why we need AutoZar. Why was AutoZar formulated? What purpose is it solving? We will also discuss about the layered architecture of AutoZar. And we will also talk about the design and communication of software components in AutoZar, primarily from a system level. We will also cover details, further details of AutoZar in the future webinars, which I'll take you through. But as of now, today's webinar will focus on these 3 topics. So when we have an existing scenario, what is the need for AutoZar? Before we go on to answer this question, I assume that all of us understand what a CAN network is, what an electronic control unit is, and we also understand the whole process of ECU development. So it is with this assumption that we start this discussion, because AutoZar is an extension of the ECU development process. It still uses the same protocols like legacy software development. It still uses the same protocols like CAN, LIN, or CAN FD. But AUTOSAR is primarily a process of development of the software, how it has to be developed. So I assume that you already have understanding about the CAN architecture as well as the protocols that are used in the ECU. With that context, let's get into why we need AUTOSAR. See, today, if you look at the whole process of ECU development, a modern car has somewhere between 20 to 100 electronic control units. Each electronic control unit serves for a particular application. That could be applications like an airbag ECU, there is a radar ECU, there's a tire pressure monitoring system. And each application is tightly binded with one microcontroller or an hardware electronic control unit. So if there are 100 applications that are being solved, there are usually 100, at least 90 to 100 electronic control units. So this makes the architecture of the system very complex. Going forward, it will be very difficult. So that is the primary reason why AUTOSAR was developed. So the primary reason why AUTOSAR was developed is the automotive industry was finding it extremely difficult to cope up with the growing requirements of customers. Customers' requirements were growing day to day, and more number of electronic control units are being introduced in the market. No longer are we in an age where we just have mechanical components. Today, 90% of the car is actually controlled by electronic control units, directly or indirectly. So in order to manage this complexity, AUTOSAR was formed. That's the first objective. And the second most important objective from a commercial perspective is whenever an ECU was developed and whenever the hardware was replaced, then the whole process of development of the software again will have to go through the same process. Right from application to basic software, everything had to be developed. So there was a total cost that was the total cost of the ECU kept increasing higher and higher. First, second, the most important thing is this application software which they had built. Let's say, for example, for our use case, let's take an airbag ECU. OEM like Benz would have developed an application software for airbag, and that application software would have been tested over years, and it would have become very robust in their system. But suddenly when the hardware is changed, what happens is the whole application has to be scratched, and it has to be written from the scratch. And it again has to go through the same whole process of testing, rigorous testing, before it becomes robust and enters into the market. That was a very serious challenge the OEMs were facing. The second important challenge, again from a commercial perspective, was the BSW standardization. BSW is more of what we called as the basic software. So whenever you build an application, again, let's take an airbag use case. So whenever we're talking about an airbag use case, it's not just enough you build the application software. This application software has to work along with the hardware. So it's usually a microcontroller with a CAN or whatever protocol that they use. So it also is important that the application software communicates effectively with the hardware. So there are drivers that needs to be attached. There are also a CAN stack that gets attached, which manages the memory. You need to manage the memory of the microcontroller. You need to manage the operating system if something is involved. All those things had to be managed. You had to perform diagnostics. So application software does not come alone. It also comes along with the basic software, which couples the application software with the hardware. And every time a new hardware is replaced, what happens is the OEM had to pay for not just for the application software, but he had also to pay for the basic software. So the OEMs did not want to actually pay for the BSW. They just wanted to pay for the application software. That's another reason why the AUTOSAR was developed. The third and most important thing is, again, it's respect to the hardware. Any application that is built in the legacy software development mechanism was tightly coupled with the hardware. The whole objective of the hardware, AUTOSAR, was to decouple the application software from the hardware. That was the first thing. And secondly, Also, from an application software development perspective, let's put it that way. If I have to develop an application software, it's not just important that I have to be very strong in how it has to be developed. I also have to have an understanding about the microcontroller that along which this application software has to be developed. This is a major problem with the legacy system. But in today's scenario, with AUTOSAR being introduced into the market, as an application engineer, I don't worry about what is the microcontroller, because my application is no way related to the microcontroller. That's the next important thing. And this also provides opportunities for industries to flex their muscles in different areas. Say, for example, you as an organization could focus exclusively on application software development, or you as an organization can work exclusively on BSW. So that flexibility is also being introduced by AUTOSAR. And the next important thing is reusability of functions. Like I said, just as I had mentioned, when you replace something in the hardware, it becomes difficult. You will have to write the software from scratch, one. Second, even if you need to add a small function to the existing ECU, it literally becomes very difficult in the existing legacy systems. The next and most important thing why this AUTOSAR was developed is the standardization of exchange formats. Here, say for example, a OEM may not buy, if he's building 100 ECUs, he may have 10 suppliers to build these electronic control units. Though a database file is shared by the OEM, every supplier will build the application in his own exchange format. A small example for an exchange format could be like, say, for example, even data exchange format. Say, for example, one application software developer can use a metric meters per second. Another application software development can use kilometers per hour. So there is a difference there. And also in terms of how they map the memory and how they communicate between the hardware and how they communicate between the application layers, there were a lot of challenges. There was a lot of discussions that had to be taken care of. But AUTOSAR is in the process. I wouldn't say it is standardized, is in the process of standardizing the whole exchange format. We will look into how it is being standardized. So every supplier will have to write the software in that particular exchange format. So that is the whole purpose of AUTOSAR. Like I mentioned, primarily to separate the application from the hardware and make it independent, and also to build very strong application software, because once you keep testing the application software and it comes to a robust state, it's a very bad idea to scratch it and rebuild it from the scratch, especially when you change the hardware. So AUTOSAR was built by a forum of all these big OEMs, tier 1 companies, and stack developers. I'm not going into all those details because you could take the Google for all these things. We will talk more from a technical perspective. So I come to the same, to summarize this whole point again. The whole purpose of AUTOSAR is to decouple. If you see, you have the application software completely decoupled from the hardware through an intermediate layer, which is called the AUTOSAR layer. Whereas in the legacy system, the software is tightly coupled with the hardware. All right. So now an OEM can actually buy, let's say, for example, an OEM wants to buy an airbag ECU. He can actually buy the airbag application software from, say, Ansett. He can actually ask a company like Bosch to build the BSW, or Conti to build the BSW for them. And they can buy the microcontroller from Infineon. All these things can be bought from different players and they can all be coupled together. Let's see how it's being done. But AUTOSAR provides this flexibility, which was not permitted in the previous or in the legacy systems. So that's a quick background about why AUTOSAR is being used, was developed. We'll move on to the next topic, which is the layered architecture in AutoSAR. Like I said, AutoSAR by itself is a layer that is being introduced between the application software and the hardware. Now we'll go into the details of the AutoSAR. So AutoSAR primarily has three layers. It's got this application layer, which is on top. It's got the runtime environment. That's the second layer. And the third layer is the basic software. This is the third layer. And we have the microcontroller at the bottom, which is the hardware unit. So the AutoSAR architecture is basically classified into three layers: application layer, runtime environment, and the basic software. The basic software in turn is divided into smaller layers, four smaller layers: the service layer, the ECU abstraction layer, the microcontroller abstraction layer, and the complex drivers. Before we go on to the software components, let's try and understand these layers in a little detail and what services they provide, and then we will move on to how its software is being developed. So let's start with the basic software. So the basic software, like I mentioned, is divided into four smaller layers. The violet one indicates the system services layer. The green box here indicates the ECU abstraction layer, and the pink box actually indicates the hardware abstraction layer. And we also have something called as a complex drivers. And if you look at some of the services that are offered by these layers, especially the service layer, takes care of the diagnostics. It manages the operating system. It also manages the memory services. It also takes care of the communication stack and also the crypto services or some kind of a security that is being introduced. These are some of the services that are offered by the service layer. And in terms of the ECU abstraction layer is responsible primarily for separating the application from the ECU. So ECU abstraction layer helps you keep the application layer independent of the electronic control unit. It's no longer necessary that one application, say for example, an airbag application has to be tightly coupled to one microcontroller or one ECU. This application airbag ECU can have n number of software components, and these software components can be distributed among the different electronic control units. Let's see how it is being done, but that's one of the main purposes of the ECU abstraction layer. And the major purpose of the microcontroller is to make sure that it gives the hardware access. So let's go into those details. So like I mentioned, the basic software module. The basic software module primarily takes care of the system layer. The system layer will manage the operating system. It also takes care of the memory management. It takes care of the communication protocols. It also handles the diagnostics. UDS is managed here. And it also provides access to the input IO ports, which is done by the hardware layer and the ECU state machine, etc. etc. It also, the basic software also includes the complex drivers. Just to give you a quick background, these are some of the modules that are part of the basic software. Now let's go into each layer independently and see what function it or what purpose it solves. The first thing is the microcontroller abstraction layer, the lowest part of the microcontroller or the lowest part of the software, sorry. So the microcontroller abstraction layer contains the internal drivers. The microcontroller abstraction layer is actually provided or usually provided by the, it's popularly called as MCAL, and it is provided by the semiconductor industry, because they are the guys who configure the semiconductor or the microcontroller. They provide all the libraries that are necessary for accessing the hardware, the IO pins. The microcontroller abstraction layer will provide the interface and or the API calls, and all we need to do is to configure the microcontroller, use these API calls and configure the microcontroller. We don't have to write drivers or we don't have to write library files to configure the microcontroller like it is done in the legacy methodology. It's all being supported by the microcontroller, and this can we can configure the microcontroller just by using the interrupts and using the libraries effectively. That's the whole idea of the microcontroller abstraction layer. And this microcontroller abstraction layer also separates the other software components from the microcontroller. It makes the application layer independent of the microcontroller. All right. So once you finally choose the microcontroller, you could use this layer and configure the software. That's how it works. The next one is, I think at the time being, it will look a little abrupt. We will go into the software details where we can actually look into more details on how it looks from a system architecture level. And then it will be much more visible, and you will be able to visualize all these things in a much better way. So the ECU abstraction layer, if you look at it, it is nothing but, as I mentioned earlier, if I take a particular application, let's say, for example, airbag ECU application for that case, if I write an application layer on top of this here, and let's assume that it has around 10 software components, all these software components may not be present in the same ECU. This particular ECU, let's say this is a particular ECU, this ECU may have just 3 or 4 software components. The other software components will be available in different other electronic control units. This ECU abstraction layer will give you the API to call those modules. So that makes it independent. This provides ECU abstraction, which primarily means one application need not be coupled with the same ECU. It can be distributed among different ECUs, and to call those particular software components here, which is distributed in other, it could be in here or it could be in other electronic control units. We use this APIs that are mentioned in the abstraction layer. They are like specified APIs. We use those APIs. All right. So that is the work of the ECU abstraction layer. And a complex driver is something that is a little away from the AUTOSAR standard. It is more associated with the microcontroller. Say, for example, there are a few features in the microcontroller which are not associated with the AUTOSAR standard, and you will need these features for this microcontroller to work effectively. Then you use these complex drivers, configure those features, and use them to build their application. It has, or use them to configure your basic software, not to build application. Use them to configure the basic software. So the complex drivers are not necessarily part of the AUTOSAR standard. That's a very important aspect that needs to be taken, and it is usually microcontroller dependent or hardware dependent, and it is used only when special cases are needed, where you need to access certain features of the microcontroller which are not part of the AUTOSAR specification or not part of the AUTOSAR standard. And as I said, see, these are the 3 layers that are part of the basic software. Of course, complex drivers is also part of the basic software, but the idea is the RTE can directly reach out to the microcontroller through the complex drivers. They don't need these layers to reach out to the microcontroller. That's the beauty of the complex drivers, just in case it needs. Yeah, so it is it's drivers for devices. That's how it's a driver specific to devices. And in terms of the service layer performs a wide range of functions. First is it manages the operating system. It provides the communication stack, all the communication depending upon the protocol, FIN, LIN, or CAN. All these things are managed. It also provides you the memory access, and diagnostics is part of the service management. ECU mode management or state management, when to wake up the ECU, when to put it to sleep, all those things, everything is managed by the services layer. So this is a quick a quick recap, or this is a quick introduction to all the layers that are associated with the basic software. We will share the presentation at the end of it. You can actually go through these layers at your own pace. So that's a quick background. All right, so the next and the most important thing is the AutoSAR runtime environment. The AutoSAR runtime environment is responsible for the effective communication between the application software components and the basic software component. It is also responsible, like say here, if there is this is one application software component, and this is another application software component. If these two software components are placed in the same electronic control unit, then you don't actually have to go through the basic software to reach out to access the data from this application software or to perform some operation on this application. So these two application software components can communicate with each other through the RTE if they are in the same electronic control unit. If an application software component in ECU1 has to communicate with an application software component which is in another electronic unit, then it has to actually go through this whole process. So it has to, this application software component here will ping the RTE, and it will use all the configurations of the basic software, enter into the microcontroller, and then it passes to the bus network or the CAN network, whatever network it is, reaches the other microcontroller, and from there it picks up the data or picks up the service. So that's how it works. So the runtime environment, as I mentioned, is primarily responsible for effective communication between the software components and communication between the software component and the basic software. So it forms the interface between these two layers. So that's a very interesting and very important aspect of the AutoSAR. All right, so that's a quick background about the runtime environment. And yeah, finally you have the application layer. So the application layer or the application layer software, ASW, what do you call ASWC, which you popularly known as, is the software for which the OEM is ready to pay for. It is the actual application that is built. Say, for example, an airbag ECU is something that we've been talking for quite some time. So an airbag ECU is an application software that the OEM is ready to pay for. So you could do. So if you look at opportunities in AutoSAR, you could actually start as an application developer. If you go on to work with an OEM, or you could actually work with a tier 1 company which is more focused on building the basic software. That could be another area. Or you could be part of a tier 1 company which builds both those things. So these are two areas where you could start building your career. One is an application layer, or the other one is building the basic software. These are two areas. And the third very interesting layer is you could also go on to become a software architect after a few years, where you really understand the AutoSAR architecture, and you're part of an OEM which manages this entire which wants to build entire software architecture for its new car release. So you could be part of it. So that comes with experience, but a good place to start with is as an application engineer in AutoSAR, or as a BSW engineer here, and later go on to become a system architect. That's a career path that many of them take. In my experience, I've seen. So we will just step back once. We'll just go back one step to understand how the legacy software development today happens, and then we will move on to the AutoSAR standard. So if you look at the legacy AutoSAR standard, let's take the same example of an application, the airbag ECU. The airbag ECU is the application that is built here. A software developer builds the airbag application, and the application does not work alone. It does not stand alone. It requires it has to work in concurrence with the hardware in order to make sure it is functioning effectively. So usually you buy a CAN stack from a third-party service provider. There are many service providers which provide you the CAN stack and the CAN driver. So the purpose of the CAN stack is it will manage the sleep and wake up calls of this. It will convert this application. If you look at the development, it works in 3 layers. You have an application layer here on top, and this is the layer 2. Layer 2 is primarily the data link layer, and you also have the CAN signal which is working in the physical layer. So the application software, once it is being written, it has to be converted into messages and signals, CAN messages and signals in this case. So the CAN stack will take care of converting this application software into CAN messages and signals, breaking up into frames and sending it. And you need a CAN driver primarily to access the resources of the CAN hardware, say for example, to access the input output or to access the memory and all those things. So this is how existing legacy software is built, where you find that the application software is tightly coupled to the hardware. So this is a classic example of the CAN stack architecture in a legacy methodology, software development methodology. This is how an existing scenario will look like in an AUTOSAR application. This is how it will look like. So you have an application software component that is being developed. We'll look at what is this actuator software component rules in a short while. But you have application software component. Let's say, for example, this is an airbag ECU software component. And let's assume that this airbag ECU application has 10 software components, just for a number to be there. It's got 10 software components. Just 2 software components can be present in this ECU. The rest of the 8 software components can be distributed among different electronic control units. The ECU abstraction layer takes care of using the right APIs to call those software control units. So that is how you get access to the other software control unit, software components which are distributed in other electronic control units. And if you look at this fellow, as I said, this airbag ECU has 2 software components here, and you find an interface here. It's a AUTOSAR interface. It's a standard interface. It's a standard interface that is described by AUTOSAR. And we'll see what this AUTOSAR interface is and the types of interfaces, all those things in a short while. But this application software only communicates or picks up values or variables from these interfaces and sends values or variables to these interfaces. Operations or variables to these interfaces. It's pretty straightforward. It does not care about sending this operation to the ECU hardware. It just has to push it into this fellow, and the RTE has to manage this interfaces. If these 2 fellows have to communicate, then the RTE has to reach out to this guy, get the data, and pass it here. And similarly, if he wants to perform an operation, he has to send this request through the RTE, and it goes through this interface. So it's a pretty standard interface formats that are being defined. So now you understand that there is absolutely no reason for this application software component to communicate with this ECU. The application developer can restrict his focus exclusively to this area. He does not have to care how this data has to go on to reach on to the hardware. A basic software guy who is working in this area does not care about how this application is developed. All he has to make sure is if there is some software component here which needs to access, or if there is some software component here which needs a resource from this particular hardware, then probably he needs to configure this driver, pick up this value, or he needs to probably configure the ECU abstraction, system layer and get it, or he needs to configure that particular ECU abstraction layer, or he needs to configure all these layers, including the RTE. That's what he focuses on. His focus is primarily to ensure that an effective communication is established between the software components, and all these data are exchanged in a specified manner. He is not worried about how this application software component is developed. And from an architect perspective, he will look at the whole system level view and say, okay, this is a architecture that I want to develop. This architecture may have so many components, so many resources are required, blah, 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 etc. So this flexibility is not being provided in the legacy tool. And that's the major difference between an existing Kern stack and AutoSAR stack that we are talking about. So before we go on to the software modules, I would like to kind of give you a quick glimpse about this whole process from a tools perspective. This is from an architecture perspective. We are primarily from a theoretical perspective, I would say, but here it is more from a tools perspective. So you will primarily need 3 tools in AutoSAR, depending upon where you are working on. First is you need an AutoSAR authoring tool, and you need a SWC implementation tool, and you would also need a BSW configuration tool. There are major vendors who supply these different tool sets. So depending upon where you are working, you will actually need that particular tool. All right, so that's how it. So as a software architect, let's say for example, an OEM, the process starts here. They will start with an AutoSAR authoring tool. 3 important descriptions are important. One is the software component description. What are the software components that needs to be built? That's important. What is the ECU? How many ECUs have to be built? All those things. The ECU resource has to be important. And the system description, like say the memory management and whole other stacks. So these are 3 important areas that you need to have. And once you have the software component description, what you will do is you will actually kind of use an AutoSAR authoring tool. Let's say, for example, RTOP is an AutoSAR authoring tool, or you could use something like MATLAB as an AutoSAR authoring tool. There are quite a few other tools available in the market. You can actually use an AutoSAR authoring tool and develop the software components. You can specify what needs to be done and all those things. We'll look at all those things in a minute, and you will have you'll generate the header files. And then this header file will only be a raw header file telling you what interface and all those things. You will have to configure the coding, the logic. You can either do a model-based coding, or you could do a manual coding in C, generate the code, and you have a .c and .head file. That's how it comes. So for this, you need something like a SWC implementation tool, like say MATLAB, for instance, just an example, or you could use manual coding also. If you're very strong in C. C is a very popular language. So if you have very strong in C, you could still use C to build your application and generate your .c and .h file. The same descriptions will be, the OEM will provide this description to one company. Let's say, for example, this company is Ansett, who builds the application for the ECU. Here he provides that these descriptions can be provided to a tier 1 company. So the EC description, the software description, all those things can be provided to a tier 1 company. The tier 1 company will use this ARXML file. Let's not talk about all those things in detail, but he will use this file, and he will generate a ECU abstract, and he will configure, he will buy a BSW stack. He will have a BSW stack from say different vendors, say Vector, or he could buy a BSW stack from Electrobit Resource, which is another BSW stack, or he may buy an ETAS BSW stack, and he will configure this whole RTE, OS, and all the other things, generate the code, bring these together, and then this fellow is finally, image file is fused into your hardware. All right, so this is the whole overall perspective. We will talk about details about AutoSAR methodology and how it will work in a more detailed way in future webinars. But as of now, I really want you to understand what we want to showcase is there is a difference between the understanding from a tools perspective and from the architecture or a theoretical perspective. This is more from a theoretical perspective, and this is more from the tools perspective. So where you will need 3 tools which are necessary for building your AutoSAR software application. All right. So now we'll go to the third part. We've completed 2 parts. We've talked about why we need AutoSAR, and we've also discussed or touched upon the services offered by the different layers of the AutoSAR component. Like I said, there are primarily three major layers. One is the application layer, where you call the application software. You have an RTE layer or the runtime environment. You also have the basic software. And then finally, you have the hardware. Now, going forward, let's go ahead and design and a software components for a particular use case. Now, let's go into a use case. Rather than talking from a theoretical perspective, let's use the example as specified in AutoSAR 4.3 architecture. We have not talked about the different variants of AutoSAR and all those things, more of theoretical things. I thought it's easy to get from Google. Let's not discuss about that. So I've used the reference manual of AutoSAR 4.3, where this is a particular use case that's being specified. And what we will do is we will build a system level software file for this use case. So that is something that we will do. All right. So as I told, this is a use case that is mentioned in AutoSAR 4.3 standard. It's a seat heating control use case. So what is this use case? Let me explain the case study. I mean the use case. The use case is pretty straightforward. Let's say it's a high-end car. There is a left-hand a passenger seat, which we call it as left, and there's a driver seat, which is the right-hand side seat. And if a passenger comes and sits in that particular seat and he turns on the heater, then the heater should be turned on, the seat heater should be turned on, and it has also to be indicated in the dashboard that the heating element has been turned on. So pretty simple use case. I'll run this use case again. It's a high-end car. There are the passenger seat, which we call as the right-hand seat, and the driver seat, which we call the right-hand seat, and the passenger seat is the left-hand seat. If a driver goes and sits in this seat and turns on the heating element or turns on the heater, and he sets the temperature to say 26 degrees C, then the seating element, the seat heater has to be turned on, and it also has to be indicated in the dashboard that this heater has been turned on. Just give me one moment. It's a quick water break. Yeah. So for this use case, there are 7 software components that are available to solve this use case. There are 7 software components. I'll break these software components. We have a seat heat dial front left. This is the dial which the driver turns on, setting the temperature. There is a seat heating controller. There is a heating element. This is an actuator. All right. This is a actuator. So this is a heating element. I'm sorry. This is the heating dial, where the driver will kind of turn this dial to set the temperature. And this is the controller, and this is the heating element. This is for the left-hand side. And the same thing goes for the right-hand side. This is the right-hand heating dial, where the driver can, this is the driver's thing, the right-hand seating heat control, and the heating element. And we also have a power management controller. So trying to understand what is the power that is being used and all those things, battery stuff like that. All right. So this is the whole use case that we have that is defined. The OEM has defined, let's say for example, and as a system architect, what I have done is based on the use case, I have developed a AutoSAR software architect here. I'm system level file here, which says that I have 7 software components, and these components will be able to solve this purpose. That is, what is the purpose? As I turn on the temperature to 20 degrees, the seat temperature should go to 20 degrees, and it should also indicate in the dashboard that the temperature is 20 degrees. Pretty straightforward. Yeah. So that is it. So as I said, we have 7 software components. I'm going to break these software components now. Let's take one software component that we talked about, the seat heating element. This is the seat heating element software component. All right. So this is one seating heating element component that I'm talking about. All right. So this seating heat element has ports. All right. So I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 ports for this seat heating element. All right. So if you just, I just missed one point. I thought I'll just add this. You look at this software component, it's got a square box. Look at this guy, it's got something like this, a dial, all right? So this symbol means it's an application software component. This symbol means it's an actuator software component. All right, so that's, there are different types of software components. Like we have an actuator software component, we have sensor software components, we have application software components. We have so many different software components that are specified in the AutoSAR interface. Let's talk about those things on some other occasion. But as of now, for our use case, we are only using these two software components. So there's an application software component and the other one is an actuator software component. That's why there's a difference in this symbol, all right? So each software, this application software component, I call this as an application software component because of this box, it's got 8 ports, all right? So what is a port, all right? So a port is a means or is a route through which a software component will access data, or it is the route through which it will provide operations. I'm talking about only from an application perspective. There are a lot of other ports, like say you have these 2 ports and all those things. I'm not going to talk like say parameter ports, other ports. I'm not talking about all those ports. I'm going to restrict our conversation to only 2 types of ports. One is the client server port and the other one is the receiver sender port. These are the 2 types of ports that I'm going to talk about. While you develop this fellow, this is how it has to be developed. So we're going to only touch upon these 2 types of ports. So in this 2 types of ports, the client server port and the sender receiver port, the purpose of this ports is it through a sender receiver port, a software component can read or write data, or it can access or send data through a sender receiver port. And through a client server port, a software component can request for operations or service the operation. It's a pretty straightforward thing. I'll repeat this. We're going to talk about it in detail, but I'm just trying to touch base upon it this is a, if I talk, this is a sender receiver port. I talked about it. This is sender receiver port here. All right. A sender receiver port, you can actually read or consume data elements. And this is a, what do you call, sender receiver port again. Here again, you can read or consume data elements, and a client server port is a fellow where you can actually provide operation or it can request for an operation. Now, this fellow, this software component, all right, requires some inputs and it will do some outputs. Any software component will take some input, process that information, and it will provide an output, right? So this fellow will require some input. Let's see, let's go into the ports later, but for the time being, let's talk about what is the input that will come into the software component. The first input that comes into the software component is whether a passenger is sitting on the seat. Even when somebody turns on the dial on the right-hand side, the heating element control, this software component should check whether a passenger is first seated on that seat before it turns on the heating element. So he needs an input. So that's the input. It gets this input from the seat switch port. It gets this input from the seat switch port, right? Second, setting of the seat temperature dial. So once a driver sits on the right-hand side and he turns the temperature to 20 degrees, this fellow, so look at this fellow, he will turn on the temperature. This is the software component here. He will turn on the temperature here to 20 degrees. This information has to come to this software component, right? It comes through this port setting. It comes through this port setting. All right. Then there is a third input from the power management. It gets some data. So it is available through this port. So these are the three inputs to the software component. Status of the seat switch. Second is the operation request from the seat heating dialer to turn on the temperature to 20 degrees and some data from the power management. The output, it will send two outputs. One, once it gets this request, it will turn on the seat heating element so that the coil gets heated to 20 degrees C and the temperature is maintained 20 degrees C. And the second, that is done through this port, what is we call it as the heating element port, as mentioned here. And the next one is the dial LED, where once this heating element is switched on, it will show the temperature. What is the temperature through this port? It will send the value through this port. It could be say on, or it could be a simple use case like say turn on off, or it could actually showcase what is the temperature. It depends upon the company or the OEM. So these are the three inputs and these are the three outputs. All right. So as I said, this software component will get a request here. Say for example, this setting. This is a request from the heating dial from this fellow. When the driver turns it on, he's getting a request to turn on. So he's getting a request. So he can get a request or he can ask for a request. Now here this heating element, if you look at it, this fellow is asking the heating, he is asking this heating element to be turned on. So you can ask for a request. So the other thing is it can take a variable, it can read a variable, all right, or it can write a variable. Here it reads a variable from the seat switch seat switch status, whether there's somebody seated. Here it will send an information to the dial LED saying that the heater element is turned on. It could be a Boolean operation, right? So it could read or write, or it could actually request or what do you call request or server request. So these are the four operations that are possible by a application software component. All right. Okay. Now we talked about ports, right? And we talked about two things. Whenever you want to send a variable or receive a variable, always use when designing a system architecture, we should always use a sender receiver port. When we want to request for an operation or we want to serve a particular operation, then we use a client server port. All right. So when we want to read or write data element, you will actually use a sender receiver port. This is the symbol for a sender receiver port. Okay, see, this is the sender receiver port symbols. And if you want to write or read operations, if you want to request for an operation or serve a particular request, then you will have to go to use a client server port. Okay, so these are some client server ports that you look at, right? So the port, now we saw about sender receiver port and the client server port. Ports can also be classified into two ports. One is R port, like what we see, and we also have a P port. All right. In a client server, in a sender receiver, if it's an R port, all right, it means that it receives or reads data flow. So R port, if you look at it, it is looking into the software component. See, this is looking into the software component. This fellow is looking into the software component. So an R port will read data from the interface. R port will read data from the interface. What happens here? So this is what it is mentioned here. Look at this guy. This is a provider port. This fellow provides a value to the interface. All right. So this fellow is called as a P port, provider port. All right. So this fellow is called as a P port. So if you send a variable or receive a variable, you will use a sender receiver port. If you send a variable, you have to use an P port. If you want to read a variable, then you have to receive a R port. All right, so this is the basic idea. All right, now we talked about the second operation. The second thing, instead of a variable, you can request for an operation. A software component can request for an operation, or it can serve an operation. So if it requests for an operation, you will use for a client. Whenever you want an operation to be done or served, you use a client server port. But when you request for an operation, you use an R port, primary meaning that it is a client port requesting for an operation. And when it provides an operation, you use a P port. All right, see, it provides an operation. So this is a P port. All right, so here this fellow is provide. If you look at this example, quick launch, just to make sure. See here, this software component is requesting an operation from the heating element, saying that please turn on the heater to 20 degrees. So it is a request. So this fellow is it's an operation request. So this fellow is the requesting fellow. So he is a client. This fellow is the server which provides the request. So here it is marked as server. On the other hand side, look at this fellow in the same software component. Once you get this information, he is requesting to turn on the heater. Now this fellow is requesting this actuator to turn on the heater. The control element is asking the heater to be turned on, the coil to be turned on, right? So this fellow is the fellow which is requesting the fellow. So here again, you use a client server operation, but here it is a client. Here you will use a server because this fellow is the provider. He is providing the service. Let's look at this example. This is a sender receiver interface. He is sending the value of this LED, that is whether the LED is, whether the heating element is turned on or off. So he is writing this information or sending this information, and this fellow is reading the information. This fellow is reading the information, right? So these are the type of ports, and these are something which we called it as client server port or sender receiver port. So you either choose a client server port or a sender receiver port primarily from the fact that whether it is based on the operation or based on you're going to read or receive a variable. All right. So I think this is a quick background. All right. So quick recap. See, this fellow is requesting this fellow is sending the seat switch is one. He's sending a Boolean operation to this fellow, saying that from the seat switch, that is whether a passenger is seated or not. This is a sensor. Once this fellow is sent, once this fellow is on, once a passenger is seated, this fellow will become one. This information is sent to this guy, and he will pick it up from here. All right, so that's how it works. And this is a client server example that we talked about, and I mentioned it works in the terms of operations. All right. So if you design a hardware, if you want to design a system level software component, you will need these elements. We are talking about, we need to understand 5 elements. The first is ports that we talked about. We have to understand what is a client server port and what is a receiver port. That's the first thing that we need to understand. The second we need to understand is runnables. What is a runnable entity? Okay, a runnable entity is nothing but a small piece of code, which is a live piece of code. It can be executed on request, or it can be executed periodically depending upon the use case. So it's nothing but a live piece of code. A virtual function bus. A virtual function bus is how these software components communicate in a system level is explained with the help of a virtual function bus. And we'll talk about a virtual function bus in a minute. But before we go to that, we'll touch upon what is runnable and an atomic software component is. An atomic software component is the smallest software component that can be written. Like say, for example, we talked about one software component can be broken into 10 different software components. And an atomic software component is the smallest software component. You cannot split an atomic software component between electronic control units. An atomic software component can reside only in one electronic control unit. That's the clear objective. All right. This is what we call it as an atomic software component and a runnable. the smallest entity. Say here is the use case that we are talking about. You have a request from the seat switch asking you to kind of turn on the LED. This is the runnable that we are talking about. You have a request from the seat switch asking you to turn on the LED. Once this fellow is detected, once this element is detected, a passenger is detected, this fellow will call on this runnable. All right. So this this atomic software component primarily has two runnables. All right. One atomic software component can have one runnable or many runnables. That is okay. It could be a complex algorithm also. But if you define one atomic software component, this atomic software component cannot be split in among different ECUs. This atomic software component cannot be split. So this is exactly one smallest atomic software component that we are talking about, right? So let us say, for example, this guy is requesting for switching on the LED. You get a trigger from this setting. Setting is through the setting you get a request saying that this is a provider port, right? So this you get a setting. You get a request from the dial LED saying that turn on the heating element. Now, once you get this request, it will go on and execute this runnable. All right. So the first step in this runnable is it will go and check whether the seat switch is turned or not. That means whether the passenger is sitting or not. This is a small runnable. You can call this as an atomic software component. You can call this small function as an atomic software component. The idea is this atomic software component cannot be distributed among two ECUs. This software component has to be inside only one ECU. This software component has two runnables, like say one mine cyclic that this fellow will keep calling from the RTE every say 1 second, for example. Every 1 second there can be a signal from the RTE asking this runnable to be executed. Just a use case. But the idea is when there is a request from this port, this fellow goes and checks for the status. This going and checking the status of the LED is the smallest component that can be written, which we call it as an atomic software component, and this cannot be split among different ECUs. All right. So we'll scrape through this for time being. The idea is, see, AutoSAR supports multiple instantiation. See, this is one software component that we can write a code. Whether you can write, there's a left and a right seat heating control element. Both these pieces are going, codes are doing the same functionality, but that the interfaces or the accessing variables will be different. So how it can be done is instantiation can be done. That is, this code can be duplicated in another memory location so that these a different set of interfaces can reach out to these guys and get the data. So since we're running out of time, I'm running it fast. Maybe I'll take last 3 to 5 minutes and finish this off. I'm sorry, I've exceeded our time limit. So this is a virtual function bus. From a system perspective, I just want you to have a look at it. From a system perspective, these are the 7 software components that we designed. All right, these are the 7 software components. Let's look at this example. The software the heating dial element will reach out to the heating control element through a client server interface that's been marked here. This fellow, once he turns on the LED, that is being communicated to this fellow through a sender receiver interface. He will once he gets a request, he requests this the heating element, the actuator to be turned on. So it goes through a client server port. And he also accesses memory from the power management. Also, so this is the 7 software components, and this is a virtual function bus. From a system level, we call it as a virtual function bus, but in actual implementation, it will be an RTE. It's a RTE, but here we call it as a virtual function bus. So that's the difference between virtual function bus and RTE. RTE is an actual piece of code. Virtual function is just a schematic diagram, as we have seen here, a system level diagram. All right, so this is the last slide we have come to. we were talking about these application software components. One, two, we have like say, an application software component and all those things. Remember, these application software components will communicate only with the interface. All right. So if it is, say, for example, it's a, what is this interface? Okay. We had looked at this application software, one heating element application software component we had talked about. It had 8 ports. If you look at, go back, this guy had 8 ports, right? This guy had 8 ports. These 8 ports together is called as an interface. These 8 ports together is what we call it as an interface. So this application software component will only communicate with this interface. And the RTE will again communicate only with this interface. There are 3 types of interfaces that are being specified in AutoSAR. One is the AutoSAR interface, what we talked about, which is associated with the application software component. This is nothing but the ports. All the 8 ports together can be an application software component interface. The second one, second interface is what is called as the standardized interface. A standardized interface is responsible for communication between the RTE and the basic software, all right, or between modules of the basic software. If you want to communicate, you can use the standardized interfaces. Standardized interfaces are nothing but API calls. They are nothing but API calls, all right. And if the runtime environment has to access the service layer, only for the service layer, like say, for example, the memory layer, memory services, or the COM services, or if it needs to access the operating system, or it needs to access any other service layer, UDS, diagnostic services, then it uses this interface, which is nothing but the standardized AutoSAR interface. Standardized AutoSAR interface actually means there is a set of syntax and semantics which are employed through which you can access the data or get the data. So that's pretty much that's described here. You can read it into your own pace. So just to summarize, we have talked about all these guys. We have talked about application. We saw why AutoSAR was necessary. I said mainly because of reusability to provide strong AutoSAR components. And we also talked about the different layers of the AutoSAR, the BSW, the RTE, and all those things. And we also talked about the last is building a system level application layer software component, where we talked about ports, we talked about virtual function bus, we talked about RTE, and we also talked about interfaces, runnables, and atomic software components. These are certain things that we talked about, terminologies that we talked about in our discussion. That's a quick background. So our future plans is every first month, on Thursday between 3 to 4, we want to have a webinar on AutoSAR. Not on the theoretical perspective. We want to go into details on how do we build a real application level software component or a BSW software component for in AutoSAR standards, helping the whole community learn AutoSAR in a very easy process. That's the whole idea that we want. And we also want to start a AutoSAR learning group, which includes all these players, the semiconductor industry, Tier 1, OEM, service providers, and universities, making learning much more easier. And as part of this learning group, we also would like to, from ANSET, we would like to commit that we will deliver series of webinars every month, first Thursday. And we are also on the process of building an AutoSAR learning stack and an AutoSAR learning kit, and also tools to support the AutoSAR community. So that's something that we are doing. And in the next webinar, what we will be, we'll look at how do we build an application software component, primarily from a system level. That is, as a system architect, how can you create an AR XML file? We'll help you generate for the same seat heating element example we talked about. We'll create an AR XML file. We will generate the software component and see what is actually a port in C. How do we access these ports and all those things? We can show you a demo of all those things. So that will be for the next webinar. And a quick word of mouth, we are launching our EDB editor on August 15th as part of our AutoSAR development community as well, as part of the community. So what is an EDB editor? This is a small UI of the EDB editor. It is a database file. You can actually create a CAN database. It is powered using the CAN tools of Python. You can actually create your own database files. You can actually create it with Excel, convert it into any format, vector format. You can convert it into a .dbc file. You can create it into an ARXML file. All those conversions can be possible. So the whole objective is we can teach you how to, you will learn how to create a database file using Excel, and you can convert this Excel file into any other file format. It's a pretty straightforward, and it is as per industry standards. You can include all the signals, and you can include all the messages as that are used in CAN. And one other feature it also supports is if you have an existing DBC file and you want to convert it into an ARXML file, you could still go ahead and do that. Instead of manually typing all those things, you could do that. It supports, the EDB editor also supports that. These are some of the features that like whatever I discussed about is there. And this is what we are. We are present in Coimbatore, Bangalore. We have a small presence in Germany and US. Thank you so much. You've been really wonderful audience. If you guys have time, I'm open for questions. I think that's pretty much from our side. We can use the next 10 minutes or so. If you have any questions, I'll be more than happy to answer those questions. Thank you, gentlemen. I also have with me my friend Malay. If you have anything to say. He's been inspiration behind this whole AutoSAR learning group. So I thought it's important just introduce him. Any questions? Yeah, we have a question from Mr. Atin Subramanian. Bhishma, can you please coordinate? And we have a question.
Yes, Karthik. We have a question from Vishal Naidu.
Yeah.
Is that the safe memory partition is available only in the main controlling microcontroller, I mean in hardware layer?
It depends upon the MCAL. It primarily depends upon the MCAL and the BSW stack that you are using. It can sometimes, say for example, you buy a BSW stack from Vector, then Vector provides the supports or works with certain hardware, and sometimes it may not be available with the BSW stack. So what you could do is you can the hardware layer will actually come with the MCAL. So there you will definitely have that. So if you're not able to do it with the BSW stack, you can definitely do it with the MCAL for sure. So it primarily depends upon the BSW stack that you're using. That's the answer I have. Hi sir, I have an anonymous attorney. You have been runnable. What do you mean by runnable? Is nothing but a C code. It's let us say for example, let's say for example, if I have to call this, yeah, this is an example for a runnable. See, this is the runnable. Say for example, this is a function, right? It's a function, and this function will go and check the status of the interface. Here you will have an interface. In this interface value, it will go and check what interface is nothing but a port. All these ports together form an interface. So it will go and check the value in this port. If this value is 1, that means there is someone being seated. If the value is 0, that means no one is on the seat. So it's as simple as that. So it is a runnable. So an atomic software component can have one runnable or it can have many runnables. This is one runnable. Let us say, for example, you are adding this atomic software component, you are adding another function which says, go and turn on the heating element. If this value is 1, then you go on and turn the heating element. That could be another operation. So that could be another runnable. So now your atomic component will have another runnable added to it. Sir, AutoSAR is open source. AutoSAR architecture is completely open source. The idea is Shivank. If you are there, just to answer your question, AutoSAR architecture is completely open source. You can download all the files. Like say there are like, as I said, there is a 25,000 page file. You can go ahead and download the file, and you can find out what is the structure, all those things, what is the format and all those things. You will have to code. Everything is open source. If you want to create, see what happens is in an existing scenario, let us say, for example, you create a database file. It is completely tool dependent. You cannot use an Excel sheet to create a database file. If you're using Vector as a software to build your ECU, then that database file has to be created in a DBC format. Or if you're using a Busmaster, it will require a different format. All right. So there are different formats which you can create a database file. But now with AutoSAR, what happens is that is completely eliminated. You will be creating a database file only in an ARXML format. But it is not open source. The tools, I told you there are three, you need three tools to develop an AutoSAR. One is base software, another is for the application software development, and the third is for AutoSAR authoring tool. These tools are not open source. These tools are not open source. You will have to either buy these tools, or you will have to be part of a company which builds these tools on their own. Some companies have their own tools. Like we have our own tools for certain applications. So that is part of it. Okay, how to build, create block coding that you used in an example. Okay, this is again a very interesting question. See, this block coding is like what I said, you can actually do it in a diagram. You can actually, like drawing it on a paper, if I have to put it that way, you can take a paper and draw this. This is how it has to be done. If you want to convert it into a what you call usable code or a XML file, then you have to use an AutoSAR authoring tool. Let's say, for example, RTOP. RTOP is an AutoSAR authoring tool, or MATLAB is another AutoSAR authoring tool. You can use RTOP to kind of do this authoring. You can create this whole virtual function bus. You can create these interfaces, which we will be demonstrating in the next class or in the next webinar. We will exactly show how this software component, this block coding that you're talking about, is converted into actual XML file or a database file. All right, so that is something that we will do. We'll tell you how to create it. There are different methods. You can use model-based authoring, or you can do tree-based. RTOP uses a tree-based structure. There are even coding-based structures. There are different methodologies available, but you definitely need a tool to do it. That's the underlying point. Sudarshan Reddy has a question. Is port will be different from multiple instances of executable? Not necessarily. The port will remain the same. All right. So let us say, for example, if you're using a client server port, you can still use a client server port here. Or you use a sender receiver port, it will still remain the same, but it will be stored in a different memory location. So if a right hand dial wants to access that port of a right hand controlled element, it will use that memory location and pick that value. If a left hand dial wants to do it, it will do it. So port is nothing but as I said, a variable. Port can be a variable, right? It could be a Boolean operation. So if the software is stored in a different location, it can actually access the memory through the BSW. You can actually access it, or through the RTE you can access it. So it's not a problem. I think that's the answer to this question. I missed the question. Yeah. How to create block coding? What is exclusive area for? There's nothing called an exclusive area for a software component. It's just it's memory location. If I have to put it, it's a memory location where the memory has where you put the software component. That's the exclusive area. So that is what that's to anonymous attendee. Girish, if one input changes, then in which layer and what changes we need to do? Okay, see, let us say, for example, in this case, if I have to take this value is 0, that means no one is seated in this element. That means this interface value becomes 0, or this port value will become 0, and this application layer will go on and turn off the heating LED, because I mean it will turn off the LED, as well as it will turn on the actuator to switch off the heating element, correct? So it is actually written in the application layer only. So this whole logic is written only in the application layer. How you access the data and how do you send the data from one software component to another software component, or how do you access the data from the microcontroller? How do you send the convert the software into a CAN signal or LIN signal and send it? That is the work of the other layers. But the whole logic about how it has to work is managed in the software. I mean, in the application layer. All right. And DaVinci developer is more of a authorization, not AutoSAR authorization tool. It's more of a AutoSAR authoring tool. It's DaVinci configurator is more of a BSW tool. So if you want to buy a BSW stack, then you might probably buy a what do you call DaVinci configurator. Yeah. As a beginner, how to start? Yeah, I think that's a pretty interesting question. You can start by from the virtual function bus. You can go to AutoSAR. Different tutorials are there. AutoSAR 4.3 standard. You can start and you can actually pick up the virtual function bus. And AutoSAR methodology. That's virtual function bus is a 150-page document, and the AutoSAR methodologies are the 35-40 page document. So you can probably start from there, and as and when you progress, you can reach out to us for some help if you need, or I think that's a pretty good place to start. Yeah. We'll share the presentation, we'll do that. Could you give BSW training on paid version? We can definitely explore that. Yeah, we can do that. We will try whatever is possible. We'll try to organize in a non-commercial way. That's our objective from a learning perspective. Will there be any training tools? Yeah, we'll definitely do training on tools. We will do it. In fact, from our next session, we will start training on tools. We'll start with an authoring tool. And then once you understand the system architecture level, then we will go on to an application level where we develop an application software and put it in an interface. You will really understand how this interface is and all those things. And then finally, we will go to, so we are doing a layered approach. First, we'll go up. We will talk about application, and then we will come down like a base. So we'll definitely give all those introduction level trainings at a free of cost. That's the whole objective of the community. Is there any help? Oh, there are a lot of help documents. Unfortunately, AutoSAR, you don't get help. RTOP especially, no. I don't think RTOP is free. I know you can get, but the best way to learn RTOP or you to do is in the next seminar, we'll definitely help you with the first level hands-on we can give you. That's one thing. If you have an RTOP, you can follow us. The second methodology is the best way to start is, as I said, you can actually read these two documents, the VFB document and the AutoSAR methodology, and there is an SWC component. There is a document in AutoSAR as well. So these three documents, if you study, the SWC document is a good 600-700 page document. If you study those three documents, you can actually start playing with RTOP. You don't need help, but you definitely need to study these three documents. I don't say we'll have to like say understand each and every word of it, but the idea is you need to know how it works. And from there, you can actually click and I mean, you can. We will also teach you how to read the AutoSAR documents so that it makes life simple for you. Yeah, I think. Yeah, thank you, Malay. Malay is also kind of answering a lot of questions. Yeah. Thanks, Malay. And I want to thank all my friends Malay as well as Bhishma and our whole team, Prashant and our whole team for trying to bring this whole AutoServe working group. That's pretty much from our side. Thank you so much. It's been a wonderful session. We look forward to hosting more sessions and making you all good experts in AutoSAR. That is something that we aspire to have as part of the working community or the learning community. Thank you so much. Mali, can we wind up?
Guys. Yeah, it was amazing. Actually, the turnout was really nice. Thanks for coming on a weekday in this hour of the day. I hope the session was interesting. And like Karthik said, please keep expecting a lot of stuff coming from our side. As Ansett has always grown as an open source company, and that's what we want to do with AutoSAR also, and not really look at it from a commercial point. And drop all your emails that you have, and I'm sure Karthik and his team will come back with all the required answers for the same. Thank you.
Thank you. Thanks, guys. Have a nice day.
Thanks, guys.
Thanks, Bhishma. Thanks, Prashant. Thanks, Malik.
Bye-bye.
Oops.